Hello, everyone. My name is William Cramer, and I'm a postdoc at Arizona State University. I'm going to be talking to you today about some observations of ram pressure stripped gas falling back. So first, I'm going to begin by defining ram pressure. Ram pressure in its simplest formulation can be understood from the Gunn and Gott criteria from their 1972 paper, whereby if the density of the ISM gas times the velocity squared difference between that gas and a galaxy exceeds the surface density of the ISM times the gravitational restoring force of that galaxy, then you can strip gas out of the galaxy. And since the gravitational restoring force is strongest at the center and weakest at the outskirts, ram pressure results in an outside-in stripping of gas in a galaxy. Now, if ram pressure decreases in some cases, or if gas rotates to a more shielded side of the disk where it feels less strong ram pressure, that previously stripped gas can fall back on the galaxy. So, for example, here's a movie from Stephanie Tonneson showing a galaxy in a wind tunnel. And if you look closely, you can see some gas ends up below the disk where all the gas in the disk was originally at zero. So some of that gas is falling back and punching through the disk to the other side. This is more apparent if I just show a still screenshot from the high resolution run of the simulation. And you can see clearly indicated by the arrow that some gas has fallen back, punched through the disk onto the other side. Simulations have long predicted gas fallback. However, there's never been observations confirming that gas falls back. And we'd like to understand fallback because in particular, it affects how fast galaxies quench. If more gas is falling back that once would be assumed to be lost to the cluster. Where gas falls back and the amount of fallback also affects the structure of galaxies and overall the evolution of galaxies. Now, if we want to study ram pressure, the Coma Cluster is one of the best places to do so because it's the nearest massive cluster. It's about 10 times more massive than the Virgo cluster, so you'll see strong effects of ram pressure. And since it's nearby, we can observe in high resolution. In particular, I look at the galaxy NGC 4921, which is the most massive spiral in the Coma Cluster, in the inner regions of the Coma Cluster. It's about 700 kiloparsecs from cluster center. Here's an H1 map on top of an HST map, showing that this galaxy has a truncated H1 disk with a head-tail asymmetry that indicates ram pressure. You can see that ram pressure is incident most strongly in the northwest quadrant. So this is the leading side of the galaxy where you'd expect to see more strong effects of ram pressure versus the trailing side on the southeast, which has more shielded part of the galaxy from ram pressure. Also, I just want to note that the galaxy is moving towards us through the cluster, so any ram pressure stripped gas will end up behind the galaxy and be redshifted. This galaxy is particularly interesting because we have some very deep HST images of the galaxy, and it's close to face on with an inclination of about 11 degrees. So we can see some really interesting ISM features on the leading side. If I zoom in on the leading side, you can see all of these ISM features and the dust extinction that stand out in the HST image, such as long filaments. These are kiloparsec scale filaments of dust sticking out into the otherwise stripped region of this galaxy, sometimes with young star clumps that appear to be at the heads of these structures. There's also C-shaped concavities where some of the dust appears to have been pushed in further than other areas, indicating differential ram pressure stripping of the ISM. So there's very interesting ram pressure effects on the ISM in this galaxy. We wanted to study what happens to the densest ISM, that's the molecular gas. To do so, we had observations, observations from the Karma array that were taken by Tony Wong with about a 4x6 arc-second resolution, which is about 2x3 kiloparsecs for the primary beam. And you can see on the top right, I show a moment zero map. You can see on the leading side, in that leading quadrant, you see the strongest peaks in the CO, possibly due to ram pressure compression, concentrating and possibly stimulating the formation of more molecular gas, as is seen in other cases of ram pressure stripped galaxies. The CO truncation radius, which is shown at the bottom left when compared with H1 is pretty similar between HCO and H1. And the velocity field is shown at the lower right. And you can see it looks relatively unremarkable. It looks pretty symmetric about the major axis, which is about perpendicular. But we also got high resolution observations of CO2 to 1 with ALMA, with a resolution of about 100 with a beam of about 0.2 arc seconds, which corresponds to 100 parsecs resolution on the leading side. We just observed this leading quadrant. It's where you'll see the most active signs of ram pressure, because this is the leading side of the galaxy. You can see that we trace a lot of that structure that I was pointing out before, some of those long filaments of dust with young stars at the heads, also trace some of the C-shaped concavities. And this will all, you can read more about what we have learned about those features in this paper that will be on the archive soon. It was just submitted. But in the interest of time for this talk, I'm just going to be talking about the fallback clouds that we found in our ALMA data. So I want to discuss what observables would indicate that we're seeing gas that is falling back towards the galaxy. Well, one is the gas should be behind the galaxy because it's been stripped out of the galaxy. And you remember the galaxy is moving towards us, so any stripped gas is moving away from us. We can determine if gas is behind the galaxy via the CO to dust extinction ratio. Let me elaborate on that a little. We see dust extinction when it is in front of the stars in relation to the observer. So here is just a distribution of dust, is the blue box, and stars. If the dust is all in front of the stars, then you're going to see even more extinction than if it was evenly distributed. That will be the maximum possible extinction if all the dust is in front of the stars. In contrast, if all the dust is behind the stars, you will detect no extinction. Now, it's well known that dust and CO tend to be correlated. However, as I mentioned, if dust is in front of the stars, we'll see it in dust extinction. If it's behind the disk, behind the stars, you'll see no extinction. We made an extinction map based on the HST image, which I show on the lower right in black contours on top of the ALMA moment zero map. And you can see that in almost all places where you have CO, you also have dust, except for a few regions where there's young stars. It's hard to estimate what the dust extinction is, and particularly bright pixels. The dust extinction is approximated based on the surface brightness gradient of the galaxy. So those regions should be ignored. But I point out two particular clouds, clouds 1 and 2, which I also show at the top here, that appear to have no dust extinction associated with them, even though they're strongly detected in CO. You can see it on the top images there in the main ring of dust. CO traces the dust very well. But for these two particular clouds, there's no visible dust associated with them, suggesting that these clouds are behind the disk of the galaxy. Now, this alone is not enough to establish that these clouds are falling back. It just tells us that the clouds are likely behind the disk. To establish that they're falling back, we need to find or investigate the kinematics of these clouds. If the gas has a velocity opposite the direction of ram pressure stripping, then it's falling back. In this case, the gas should be blue shifted in our observations, although it's a little more complex than that. So to investigate the kinematics, we used disk fit to fit the rotation curve of the galaxy. This allows us to just look at the residuals with respect to what would be normal rotation. The residuals indicate, the deviation from the regular circular motion. However, they can be some combination of that vertical motion moving back towards the observer that we're interested in, but it could also be an azimuthal motion or a tangential motion or a radial motion. We note that those two clouds that you see at the top have blue shifted velocities of between 20 and 60 kilometers per second. Now, those clouds are very near the major axis, so the radial component should go to 0 because theta is close to 0. However, it could still be some combination of a blue shifted vertical motion back towards the observer, or it could be due to slower azimuthal motion. Now, we can rule out azimuthal motion in this case due to both simulation and basic physics, in that typically in simulations, gas at outer radii that's being pushed by ram pressure actually have increased azimuthal motion as they're pushed back towards the disk due to conservation of angular momentum. So we should expect these clouds, if they were actually rotating with a different velocity than predicted by the circular motion, to be rotating faster. Instead, to explain their blue shifted motion in this map, they would have to be moving at least 200 kilometers per second slower in rotation than the rest of the gas, or be falling back towards the galaxy with a velocity of about 50 kilometers per second. And we see this is a simulation from Stephanie Tonneson that's also included in the paper. This is a simulation of a galaxy that's experiencing ram pressure at a disk wind angle of about 45 degrees. So similar to what we expect is happening at NGC 4921. And if we make a phase plot of the leading side, which is shown at the bottom right, and plot that azimuthal motion on the x-axis and the vertical motion on the y-axis, you can see that there's some gas with negative z velocity falling back towards the galaxy, just as we would predict for fallback gas. But that gas is also rotating faster than the rotational motion. There appears to be almost no gas that's rotating slower than the rotational motion due to that conservation of angular momentum. So, and one thing I want to point out is these sims include no gas cooling, which could be a key component to fallback occurring that we see in observation. So there's a lot to learn still about the mechanisms behind why gas falls back. But in summary, we found blue shifted velocities consistent with the gas falling back towards the observer. So in summary, with both Karma and ALMA data, we've managed to make an approximate model of the expected circular velocity in the disk, and we found these interesting blue shifted clouds that, along with our evaluation of the dust extinction, allows us to establish that these clouds are likely falling back, are clouds behind the galaxy that are likely falling back towards the galaxy. And this would be the first observational evidence for gas fallback in a ram pressure stripped galaxy that's been predicted by simulations for a long time. I'm happy to answer any questions that you have. Please get in touch with me. Thanks.